We're going to start with 3 clicker questions, stuff we did last time. It was at the end, so we'll review, see if it makes some sense if you thought about it, help solidify it, and then we'll continue on with charges and start moving them around, making circuits. So this first one, as you're digging out, and what your clue is, it might seem more quantitative, like this is a computational problem, which it is, but it's based on if conceptually you remember what the electric field is, what it represents. Or, of course, you can look in your notes or your book to see what the formula is, but this is to help reinforce that concept of what electric field is. So as people are coming in and signing on, does anybody have any other questions while you're dealing with this one? So I didn't specify, but I figured you got it from the book. We talked about Coulomb's law, the Coulomb force, but I didn't actually tell you that the unit for charge is Coulomb. So this thing that has a tenth of a Coulomb, that represents how much charge it is. So that's the Q. One Coulomb is a whole lot of charge. Charges are small. It's just there's a whole lot of them, so it gives you a reference. Let's see. It looks like most people have settled. Should I safe to start counting? 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Most of you C, and that is correct. So an electric field, you can just look up the formula, but it is the force per charge. It's like you put a charge in an electric field and it feels a force. So it's the force per amount of charge you have. You can put a bunch more charges in. So it's F over Q is the equation that guides our thinking. And so the force is 10 newtons to hold it at rest. Why does it take force to hold it at rest? And if you didn't apply that 10 newtons of force, what would happen to the charge? I think Stephen's representing that. Anybody else? Okay, you put a charge in an electric field, what will it do? Move. Yeah, it's going to accelerate. That electric field influences it. So that's why it wants to move. You have to apply 10 newtons of force to keep it at rest. So 10 divided by 1/10 of a Coulomb is 100. Questions? I like these, and I'm trying to build it on that. This is like we've dealt before, where we had masses and we did forces and they moved and accelerated. Now we have a mass, but we're dealing with its charge, is how it's influenced by an electric field, rather than before generally a gravitational field. We'd work against that. If I held this up, how much force do I need to apply upwards to keep this at rest in the gravitational field? You don't know the actual value, but what do we call that? It's got to equal the object's weight. It's weight. That's the force that the Earth is trying to accelerate it down. So I apply a force up to this object to keep it at rest. All right. How about this one? the end, I drew some electric field lines. They come away from positive charges, if you remember, and they go towards negative.
But what about their spacing?
Maybe it won't rotate on me now, sorry. I don't know if you were here just rubbing on the microphone or not. But. So visually, if you draw some of these electric field lines from positive charges to negative charges, they can tell you something about the field strength. That's what this is asking. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Whopping majority of when they're closer together. You're right. Good. You learned that one or remember that from Friday. So right next to a charge, they're closer together. It'd be stronger. But also, if you have you could have some funky geometry, and it's cool. You could just try to draw the lines. And if you want to remember how to draw the lines, to visualize it, you might have some funky geometry. Just put in a positive test charge and think about the forces that would feel based on the charges surrounding it. Positives will repel it, and negatives it'll be attracted to. So you can just draw your little vector arrows, see which way that particle at that point would want to go, and that's the direction of the electric field at that point. Does that make sense? All right. And you can shield conductors, antenna, and things from electric fields. This was had a radio over here in a metal cage. So the electrons on the surface of the metal cage arrange themselves how? Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. We're not as sure on this one. Do you want to talk to a neighbor and do it again? Okay, go for it. Oh, the talking got quieter. All right, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. I know you haven't all voted. 3 more seconds. 3, 2, 1. There we go. All right, you're more split between A and D, but you've done that. So you realize there's shielding going on. So is the electric field inside 0? I'm hearing no's. Are the electrons on the surface shielding from external charges? The other people that think the other answer is saying no. All right. Well, see, this is good. We've narrowed it down to where what our hole is in our thinking, and it shows me that it would do us all benefit to discuss that one more. That was the last one. So, let me draw a picture. If here's a big metal conductor like our metal cage, and you have, let's say this is the center, but let's put a point over here. Let's call it point P. If you're there, or that's like the antenna, you get shielded from the external radio waves. But it's because the electrons on the surface of this conductor, they're free to move because it's a conductor, and they will arrange themselves so that the electric field is zero everywhere inside, which is why it was answer A. To see that, if you're over here, well, let's draw it like this. It's kind of like through this point, we can kind of represent it. This is a two-dimensional of a three-dimensional sphere. But from this point here, it's like it sees this charge. Let's call that B. The charge in this region. And this will see, equivalently, A. And so, which one will have a greater influence? A or B? Okay, tell me why you're not sure. Tell me what you are thinking. Got anything? Nobody's thinking anything? All right, I'll prompt you. The way I've drawn it, which one has more charge involved? A. So for that should have a greater influence, correct? You got more charge, you're going to feel a larger influence. That's Coulomb's force, Coulomb's law. However, it's farther away from A and closer to B. That's still Coulomb's law. The inverse square law comes into play because it's closer to here and it's 1 over d squared. That means B will have a larger influence. The effects perfectly balance out, as I mentioned last time and the book explains, so that the influence of more charge here but farther away, less charge, not just half though if you're shifted over there, but you're closer. So the effect here from B and A cancel each other. And that would work from any direction, if you did it this way versus this way. Or I could have drawn this like this and this, but now you're dealing with this and this, and it always works out no matter where you're at inside. The electrons have arranged themselves on that conductor such that the electric field always cancels inside. Does that help? It's something we've observed. I'm just telling you that's the way it is, and this is how to understand why it does so. So you can shield yourself, like I said, a lightning striking your car. If you're inside your big metal conductor, you won't feel the electric field due to that lightning strike. Sure, it'll deposit charge and they'll arrange themselves on the outside surface of your metal conducting car, but they won't come inside. As long as you're not touching the metal, usually on your seat. Same again with like your cell phone in an elevator. It's usually this mostly big metal cage that shields you, and anything that's reception that's trying to get in influences the charges around the elevator, and you're inside picking up nothing. So it's just an effect that we see. We can use it too to shield things. I saw somebody come when they were testing the Wi-Fi stuff several years ago. That's the router, by the way, that white box below the lights. It was fun. He built a cage and put his laptop in it to ensure that he wasn't picking up stray signals. He was purposely shielding himself so that he could get the strength for what he wanted, not for some random piece of electromagnetic wave wasn't through our airspace. You know those people that they make fun of them because you're crazy because you're wearing the aluminum foil hat because you don't want aliens or the government to be reading your thoughts. There's actually some truth to that. If you enshroud your head with an aluminum Faraday cage, these are called, metal cage, then your brain, there's no electric field reaching your brain from external sources. I mean, you look like a dork, but see, at least there's some truth to that. You couldn't probe your brain as easily if you're shielding it from an electric field that's trying to probe it. So Hollywood isn't completely crazy, I guess. All right, any questions on those three questions? Concerns? So we got charges, we got these forces, they repel, they create electric fields. Electric field is the force per charge on something. Well, let's talk about energy then. That's what I've drawn up here. So we had gravitational potential energy. I love analogies and connecting it to stuff we've already discussed. So it's not, to me, I can remember things better if I build it on a scaffolding of something I already have instead of it just being something brand new. So hopefully this will help you. Gravitational potential energy. We have a mass. What do we have to exert to lift this mass and put it up there, a distance h higher? What do you have to do? You exert a force, right? And you exert that force for the distance h, and what do we call that? Yep, force times distance. My distance is h this time. Yeah, so we did work. And work changes and transforms the energy. And now what kind of form of energy do we have up here? I hope you can guess. Yeah, we have gravitational potential energy. So it takes work to pull this mass, to lift it, to exert a force on it, to overcome this gravitational field that's trying to accelerate it down. If you just push it off, it'll naturally accelerate downward because at the rate g and come back down and lose that energy. It'll convert from gravitational potential energy to kinetic of motion. And then when it hits the ground, there'll be sound and heat, and it'll transform into that. You remember all that? Is that ringing a bell? Good. Well, it's identical with electric potential energy, these charges now. If there's an established an electric field, it's a positive test charge that tells us which way it wants to go. So this positive charge wants to go down, just like a mass wants to go down. So it takes work to lift it up, and once you're there, it has energy. What do we call it? Potential energy. It's just electric potential energy now instead of gravitational. And if you release it, it'll accelerate due to that electric field. So this is the energy. Over here, GPE or PEG if you want, is mgh. It's that mass, g, that's the force, times distance. Excuse me. This one, electric potential energy, or potential energy of a charge, we're dealing not with a mass, but a charge. This one's in a gravitational field trying to accelerate it. This one's in an electric field trying to accelerate it. And over a certain distance. It's just there it is. So you can see the similarities. Do you see that this is force? I shouldn't write it like that. That makes it look like it's part of the equation. This is F. Can you see that this is F, the electric? Because the electric field is force per charge. So you rearrange that, that's what F is. So it's still force over distance. You do work, and it gains that much energy. So that's our new equation, but hopefully not too confusing. That tells us the electric potential energy that charges have. Because that's all they do is, in circuits, when we make them flow, we store energy, and then we release it. We use that energy to light a light bulb, or run a car, turn a motor, something. Now, the new term is, since we deal with so many charges, instead of dealing with them as individuals like we usually can with masses, there's a lot more charges. We define a new term, and it is the electric potential. And this causes students no end of confusion. To specify the difference, electric potential is not the same thing as electric potential energy. The electric potential is the same thing as what you guys are probably more familiar with, voltage. When you hear the term voltage, it's electric potential. And that is just the electric potential energy per charge. So that's voltage. So our electric field is the force per charge. The voltage, or electric potential, same thing, two terms for the same thing, is the energy of that charge, electric potential per charge. And these are much easier to deal with, electric fields and voltages, when we're dealing with so many charges. So if you took a proton with an electron whizzing around it, and you want to remove that electron, that'll take work. You'll have to apply a force, because these want to naturally be attracted to each other. The electric field's in this direction, from positive to negative. So the electron, which is negative, is trying to go this way. So it would require a force and energy to pull it out. We just use this energy to move them around. Questions on that? Oh, good. Glad that makes sense. So let's do an example. I have a bunch of charge here I'm going to just call big Q, and one little charge over here. To see how we can apply that to something. So let's see. Let's do the energy. The energy is QED. The charge, this charge, Q. The electric field that's set up in there, I don't know what it is, but it's E. And we'll call this distance D. There, that was easy. So that's the amount of electric potential energy this charge has at this position relative to this bunch of charge. Yeah, this could be like a bunch of protons. Say this was like this. And somehow I removed a lot of electrons from it. So it was left net positive, but a bunch of net positives. So that could look like this. And then you can think of this as an individual proton over here, if you will, like an ionized air molecule, hydrogen molecule, atom. Let's look at the energy of this one. Let's say you have two protons over here now. So the electric potential energy of that is still the charge, but this is 2Q, electric field D. So it's twice that. If you were to grab these charges and try to remove them, that would take force. What's the force? You know what? Why don't we call this case A, and this case B, in case in your notes you're getting confused or something. The force is charge times electric field. So this one's Q, E. And this one is 2Q, E. I hope you can see that it would take twice as much force and twice as much energy to try to move this guy than this one. Because these are, the force between these, Coulomb's law, is twice as big. Do you see that? Do you remember, let me write it over here. Q1, Q2, the distance between them. So that force in this interaction pair is due to both charges. This one's not changing, but this one's twice as big as that one. So that 2 means there'll be twice as much force between these than these. Thus it takes twice as much force and twice as much energy to pull it away. But now check this one out. Let's do the electric field. That's force per charge. Okay, the force, let's put in Coulomb's law. K, big Q, because that's 1 in the interaction pair, and little q, the other one, over d squared. And all of that, because that's the F. All that's over q. So the q's end up canceling, and you're left with k, big Q over d squared. It's over q because this is F, this is F. And so we still have to keep that guy. Now I'm going to do the same thing in case B. The electric field at B is still the force over the charge, but our charge this time is 2Q. Excuse me. What's the force over here? K, big Q, 2Q over d squared. That's the Coulomb's force. That's F. All over the 2Q. The 2Q's cancel, and you're left with the same thing as in A. So what's nice is you can have bunches of charges, but you don't have to keep track of them individually. If they're in these positions with the same distance away, the electric field in A is the exact same as the electric field in B. You don't have to start counting little guys. Oh, there's twice as much charge, so it's going to take twice as much energy and twice as much force, which is absolutely true, but it's nice to say, that the electric field established in both of those is exactly the same. So is the voltage, the electric potential. I ran out of room up there. What's voltage of A? That's the energy per charge, the electric potential. Energy per charge. This energy is QED over that Q, so we have ED. And the voltage of B is its electric potential energy over its charge, which is 2Q. That energy we found was 2Q ED over 2Q. So it's ED as well. So as you finish copying that and taking it in, the force and potential vary. The force and potential energy, sorry, be clear. But the electric field and the electric potential or voltage are the same in those two cases. Yes, Glenn?
So would the electric potential always be a constant in that case, so ED?
Yeah, if we put 100 Q over here, a distance d away, it wouldn't change the electric field or the electric potential between the two. That's correct. If we change d, that will change things. So this helps because the energy available per charge is the same in each of these. This electric potential, this term voltage, we're going to start using even more. Here, yeah, I have twice as much Q over here, but it's the same amount of energy is available per charge. It takes twice as much energy, but there's twice as much charge. So the energy per charge is the same. In case B, this doubled, but this is doubled too. So the electric potential is the same. So next time, you guys hear volts all the time, 120 volts, 9 volts, 1.5 volts. One way to think of that is it's the amount of energy available per charge in whatever circuit you're hooking up. So when you plug into an outlet, does anybody already know how many volts come out of here? 220 is one. That comes out of this one. 110 is close. It's actually 120. So 120 volts. What's that tell us? That means there's 120 joules of energy available per Coulomb of charge. Because we know energy is joules and charge is coulombs. It's joule per Coulomb. That's volts. Same thing. And we can plug all kinds of different things up to here with lots of charges or few charges. But the amount of energy available per charge remains the same because it's still 120 volts. Now, if you have a 9-volt battery, now there's a lot less energy available per charge. I know, it doesn't seem that exciting yet, but I think that's kind of cool. As a kid, it was just 9 volts, 120 volts. I don't know, that's just what you plug into, and the more volts there are, seems like the more energy you could get out. But it's the amount of energy per charge available. Yeah, Mark?
Why do different places use different amounts of voltage?
Different places use different amounts of voltage. That's arbitrary, really. We end up with 120. You can have 220. It's how you design your stuff. Like so in the United States, most things are designed to run off of 120. So if you plug it into 220, you're now allowing twice as much charge available per charge. And that might be too much energy for the device you're plugging in, and you can fry it. But some devices are made that way. And it was just kind of an arbitrary value. We didn't want it too high because we didn't want to, if we touch things. But there's other reasons we're getting into why it would hurt you. But it could have been anything. This light bulb runs off of, this is 1.5, 3, 4.5, 6. So this runs off of 6 volts. Each Coulomb of charge running through this bulb needs 6 joules of energy. Plug that into 120 and it'll blow like nobody's business. I spent a lot of time on this because we're going to use voltage more and more. And I just want to make sure it's clear. Any other concerns? So our new things are just electric potential energy. But we're going to deal more with just the electric potential, the amount of energy per charge, voltage. All right. You've probably seen these before. Raise your hand if you've never seen a Van de Graaff generator before. A couple of you. These are cool. There's a motor in the bottom, and all it does is it turns a pulley that makes this rubber belt go up and down. I'll show you. You can see it rotate. And every time it comes off the pulley, it's like me pulling a piece of tape off the roll. Charges separate. So I'm using the electricity here just to provide the energy to make the things separate. Every time it comes off, its charges separate, and an excess of electrons go onto the rubber belt. Then the rubber belt comes up here and deposits them onto this conductive sphere, which is hollow. And so all the charges, they're all negative, so they repel each other and distribute themselves fairly uniformly around this sphere. And this gets charged up more and more negative as this runs. And if you get more and more charges, the electric field increases. You can visualize the electric field lines coming off, and they get closer and closer together as you cram more and more charge on here. This is grounded. Basically, there's a big metal pipe that I've seen underneath this table that goes into the ground here quite a ways. So it's like it's a ground sink connected to the big earth that can handle lots of charge. So this will remain neutral. and you can get a difference in charge between the two. Let's hold it up. You guys might be able to see better. And when there's a difference in electric potential or voltage from one side to the other, you can get these charges to flow. You set up an electric field. It's like those. There's a difference in the amount of charge between them. There's a lot of charge on one side and not very much on the other, so there's an electric field between them. And so charges, if they're free to move, will in that electric field. And so you get sparks. This is like miniature lightning. The same thing happens in the clouds. Charge builds up in the clouds, and if a bunch of negative charges form at the bottom of the cloud, what will that do to the charges in the ground? Very good. It'll polarize, like our balloon on the door. And so the negative charge in the cloud will attract the positives in the ground, and the ground where we're at is now more positive than negative. And if that difference builds up too much, whammo, lightning, just like this, trying to balance things out, going downhill. They want to move downhill, and they will if they can't find a way. You know, by the way, who asked me to keep the balloon up all during lecture? So right after class, I put it up on my whiteboard in behind here. It hasn't moved at all in the 2 days. It's still attracted. Let's do this. Let's put some pie plates on here. Those should get charged up negatively. And they're repelled off. This one's fun. Got some packing peanuts. Are packing peanuts conductors? No, they're insulators. And they're not in actual contact with the sphere. But they are going to be in the electric field of this. So any charges on the styrofoam will be influenced by this electric field. And so we can try that one. Oh, that was a good one. All right, who wants to come up and do that with their hair? I need a volunteer. Maybe somebody long hair that's fairly clean. Go like this. Let's let the charge come onto you and see what happens to your hair. Oh, all right. So yeah, we'll just get you up here. Get your hand on here where you're comfortable. And go ahead and put your right hand on there. And you'll be safe as long as you don't let go or step down. So let's do this and see what happens. So charges are building up like before. And they're conducting through her onto her hair where you can start to see it. They're the same charge. Same charges want to repel each other, get as far away from each other as possible. Best way to do that is for her hair to start standing up and spreading out. Here, give us one of these. Kind of free it up, and I'll come over here so you can see what we see.
That did it.
Yeah, if you ever feel like that outside, lightning's about to strike any moment. Yeah, take cover. Don't let go yet. All right, now that I've turned it off, she can let go. It's safe. Yep. There, did you hear that when you hit the ground?
I did, and I felt it.
All that extra charge on her left and went into the ground, and her hair has gone down. Thank you very much. So, as long as this is running, this and this are at the same electric potential. Because charges were insulated from the ground, so they remain on her. And the charges build up on here and spread out evenly. So there's really no difference in voltage or electric potential between this and this. This actually charges up to about 400,000 or 500,000 volts. You just touched 4 to 5 500,000 volts on your body. Why are you not dead? Oh, well, watch this. Charge it up. It's not comfortable, but I'm not dead. So, first of all, if there's no difference in potential, just like that, if there's no difference in gravitational potential, height, it's all at the same energy. The same amount of energy per charge. But the reason we're not dead with 500,000 volts, that means there's a lot of energy per charge. But this doesn't make that many charges, actually, relatively speaking. So the overall amount of energy involved here is small, and we don't die. It's actually charge going through our body, which we call current. Current is the flow of charge through things. That's what kills people, if you have too much of that. That is amps. Let's write that one down. So current is the flow of charge. We know what makes it flow now. A difference in electric potential, a difference in voltage, an established electric field. Current is usually by a capital I, and it's the flow of charge. So it's the charge over time. It's like the flow rate of it. How much charge is moving past in a certain amount of time. That's our guide to remembering what current is. Now, I'm probably going to fall susceptible to this, and I apologize, so my disclaimer is now. Technically, in electricity, we say current's flowing, like we do with water in a river. The water forms a current. But it's the water that's moving, not the current. Current is moving water. But we say current's flowing all the time. You can say that with electricity, and I'll probably slip and say it too. Sorry. Technically, what's flowing, though, is the charge. That is a current. And that is measured in, let's see, this is in coulombs, and this is in seconds, and that is defined as an amp, which is short for ampere, a French scientist's last name. But yeah, you've heard of amps before. That's telling you how much charge is flowing through something, at what rate. That moving charge will transport the energy because you have so much energy per charge. What do we call energy per charge? Close. It's not potential energy. It's the potential energy per charge. Electric potential or voltage. That's the electric potential energy per charge. So these are what we usually deal with in a circuit. The 120 volts we plug into, that's how much energy we're given to each of these charges. But then it's moving them through the circuit, the flow of them that actually goes through our bodies if we're in the circuit. And it distributes that energy to the light bulb filament, or to us, or to whatever, your speaker for sound. Watch this. Let's do the product of these. Current times voltage. Current is the flow of charge. Sorry. Make this a little higher since the Van de Graaff generators are in the way. That's current. And the voltage is energy per charge. What do we get? Energy per time. You've seen that before. What's it called? Energy per time. The rate at which we use energy. I know it's been a while. Work it transfers energy. I did an example over there running up the stairs. I exert the same amount of work to get up to this point. But what if I do that same amount of work, that's change in energy faster over time? We called that something. Anybody happen to remember? We had impulse and power. Impulse involved time, so you're remembering correctly, but that's not it. It's power. Impulse was, yeah, and it's an I too. Sorry. A change in momentum, which was a force for a certain amount of time. So you remember the time part, right? Yeah, this is power. Power. Power is the rate at which we use energy. Energy over time. And that's what this product actually gives us. We're delivering power. That's what you pay the power company for. You're not buying electricity. You're buying the power. So they give charges a bunch of energy and then push them out, cause them to flow in our circuits. The charges are already there in your circuit, by the way. You know, this thing, it's not like the power company, the charge is sitting there waiting to be used. I turn this on, and boom, the charge goes into all the way from the power company. This already has charges. What you do is when you flip the switch, excuse me, you immediately establish an electric field, like up there, top left. There's a potential difference, an electric potential. Could be 120 volts to 0 or whatever. That electric field, once you establish it by flipping the switch, these charges are in it, and they feel it. And it's like 1, 2, 3, march. And they all start marching at the same time. They're accelerated by the electric field. And these charges start moving. But they have so much energy per charge. And now they start flowing and can distribute that energy to this, which I'm going to plug into this. Does that make sense? I'll do that one next time. Let's do this little guy. Anybody recognize this? What is it? Monster High, yeah. I never watched it, but I saw it was on sale a couple Christmases ago. It was this Frankie Fusion recharge chamber from Monster High. And I saw the commercial, and I was like, well, this is what it does. It recharges Frankie. Well, you just saw your hair stand up. I was like, whoa. Is that a Van de Graaff generator? Are they just separating charges and creating a high electric potential, a high voltage? Sure enough, I took it apart, and inside is about the exact same thing. A belt on a pulley that spins, and it works the exact same way. She's just in the vicinity of it like you were, and her hair gains charge and goes up. This is the last one. It's called a Fun Fly stick. It's a toy. And inside it is the exact same thing. Whoops, I'm going to need this. It creates a Van de Graaff generator which charges this up, which then this light foil touches. Charge is transferred by conduction, and you can repel it. You can levitate it. Wingardium Leviosa. No, it's Leviosa, not Leviosa. Because they're repelled. They have the same charge, and so I can overcome the weight with the Coulomb force. But it's all because I established an electric potential, a high voltage built up of charge on this wand. All right, you guys are free to go. Gravity.